So today I will speak about the very first step to stochastic integration, right? So that lays the first step to stochastic calculus and applications. Maybe I will not be able to do applications, but let's start. I can do it maybe another lecture. But I would like to go a little slowly to understand about what is going on this subject. So I will cover these three sections. So first, an introduction and review about Riemann-Selges integral, and then somehow some details about integrals of Riemann-Selges, and then I will spend. Sorry. Okay, and in the third section, I will speak about the Brownian motion. So maybe I will need more time to speak about this subject. So I would like to just introduce elementary properties and definitions, and then just to consider in the section 4 just the very elementary approach to stochastic integration in order to understand the difference. Okay? So, so the main goal of this talk, the hope is that at the end we will be able to understand. So first of all, we will define what this means. This is the Brownian motion, which is a continuous process that I will define later. And we are going to understand why this integral, this object here defined, which will be defined, is different from that one. So what does this mean? So a Brownian motion or a stochastic process is a two-parameter function. One is time, another is little omega. And this little, the regularity on this little omega is only measurable. No continuity is needed for that. But for time, we will see what is the maximum regularity for that function in time. So by the way, this process is irregular, is nowhere differentiable, and continuous. So I will show you later some pictures about the plots of this, the trajectories of this process. So the first thing is to understand the difference between these. So what does this mean, this integral here? So this means that I fix the parameter omega and I integrate path by path. For each fixed omega, I make the integration. So is it possible to do this? We will see, right? So the second thing is, when I integrate this, so classically in Selges integrals or Riemann integral, if you integrate a function with respect to the function, if it is regular, then you have here the square, right? Xt squared, if it is absolutely continuous with respect to the living measure, xt squared is equal to x naught squared plus 2 times the integral from 0 to t, x dot, which is the derivative, dx, right? Xt dxt, right? So we will see that this is different, right? And then, since they are different, we should identify the difference. What is then the difference between the two, if they are not equal? Okay? And the other thing that we will understand, inshallah, at the end, that if A integrate, this is the sinus, right? Sinus of B1 with respect to dBs. This is different from that one. So this means that A cannot take outside this, even it is constant in time here. There is no S here, right? So A cannot take it outside. In another way, this is not defined. Why this is not defined? Because you have here P1. This is the P evaluated at time 1, and at the future, at the end point, the right point, right? So this means that this integration we are going to define cannot be defined for future, okay? For the future. So this is the main thing that we are going to understand today. Okay, so let's get started with Celsius integral. So if you consider a function f with some regularity that you need, for the moment we can consider it as continuous, right? And we have here an interval, closed interval. And they consider also this is a bounded function and continuous, small enough, right? So the Riemann integral is defined by this limit, okay? And of course this delta n is a partition of AB and so on. So this is, one should remark first that the evaluation here of this function is done at any time tau I between these times, between Ti or Tj, Ti and Ti minus 1. Any point in that interval, any point. Right? This is what we learned from Riemann integral, right? And we will see that this doesn't work for stochastic integration. When you have, I mean, by stochastic processes, measurable functions. 2-parameter function, measurable in one parameter, and as the maximum regularity continues for the other. Right? Okay, so this is just what we want to remember here. Of course, this is very well known. Now for the Celsius integral, if you consider a continuous function and another function j here, so of course the regularity you need for g in order that this summation or this summation converges is that j is of bounded variation. So G is a bounded variation means only that J is the difference of two increasing functions, right? G, you can think about G as the difference of two increasing functions. And when you have increasing functions, of course, this induces measures, and then we can do integration. But this is important in numerics, because at some order n, I can substitute this integral by this summation, right? So this is, and this summation converges whenever f is continuous and j is of finite variation of the or difference of two increasing functions. This is Celsius, right? Okay. So so remember also that this tau here is any evaluation point between Ti and I minus 1. Okay? So that's good. Okay. Now, if the function f is monotonically increasing and j is only continuous, right? So now, this has no meaning, right? Because we have seen that in order that this object has a meaning, j, this one, should be of finite variation or difference of two increasing functions. No, I define this. I should put two dots here. As this symbol means that I put a definition, right? So now this f is of finite variation or bounded variation, and j is continuous. So to define this, I put the formula saying that the integration parts holds true. So because now this term here is well defined, this is the evaluation of the product of two functions in 2 points, and this is now the integral which is defined before, because now f is of finite variation or of bounded variation. So this is well they will define as Celsius. This is Celsius integral, but this one not, because the corresponding sum here does not converge. So I define this object as by the left-hand side, in order that the integration purpose will hold true, right? So this is how to define this integral for j which is continuous here, and this one is of bounded variation. Okay. Now the question is, for continuous function f and j, is it possible to define this when they are both only continuous? So this is the first question. Maybe I will answer 4 or 5 questions during this talk. This is the first one. Okay, let's go and see what is going on. Start with first by the very elementary one, the very simple one. What happens if f is equal to j? So if f is equal to j, this means that can we give a meaning to this integral here? So for the moment, I'm still deterministic, right? Just deterministic functions. Okay, so the question is how do we, can we define this object? Only for continuous functions. So here, so we are going to define some quantities. Ln, this means left, and this one is right. So this means that I evaluate here the function f at the left-hand side of the interval, and here in the right-hand side of the interval. Right? So they very simple things, right? So this means that tau I here is equal to t minus 1 for one, and the other is ti. Okay, very elementary, and let's see what's going on, what happens for this. So if I take the difference, so the sub question, if you want, to this one, is it true that the limit of ln is equal to the limit of the right-hand side? That's what we want to see when, of course, the mesh of the subdivision goes to 0. So let's first calculate the difference. So the difference gives you something which you can recognize, and the sum gives you something which is very simple. So actually, this summation is exactly the evaluation of the function at the endpoints of the interval. Left hand, f of b squared minus of a squared. Okay. So if we combine these two equations, we deduce Rn, right, and ln, right? So in Rn you have this difference, and you have here plus, and in ln you have the same evaluation for that one, and minus here. The only difference is you have plus here and minus here. Okay. So now when looking at these two terms now, in order that L and R has a limit, so we just need that this subject has a limit, right? So, and when this has a limit, when the mesh goes to 0, this means something, right? This is exactly the quadratic variation. The quadratic is because you have 2 here, and if this limit exists, so this means that the function is of quadratic variation. The first variation, quadratic, third variation, we can develop this, right? So this is the starting point in order to be able to do this, right? So in order that this L, Rn and L have the same limit, this should be 0, right? Because if this converges to some constant, to some L, you will have here this term plus L and this term minus L. So they will be different. So the only situation where you have this, both the things coincide, when this function is 0. Right? This quadratic limit is 0. Okay. So that's I explained here. So the limits are different. These limits are different if and only if the quadratic variation of the function f is non-zero. Okay. So then let's see what happens when the function are smooth somehow. Let's consider f is C1, right? So if prime exists and so on. So we take the difference and use just the mean value theorem, and then we can control this by the derivative, and then you have here the mesh, and you have the length of the interval here. So this means that this limit goes to 0. Say they are the same in this situation. And we can even here take, So these two things, this difference goes to 0 in this situation when f is C1. right? And the limit is equal to this, right? Then for C1 function, you have this integral. Sorry, this font does not work very well. But I mean that this is classically this one, and if you integrate, you get this one, right? So this is the transformation we have for this in the regular case. This is the regular case. This is known, of course. This is very elementary. And now the question is, suppose that if this continuous function satisfying this condition, yeah, order of order 1/2, okay? And in this case, we see that the difference here is equivalent to this summation, which is exactly b minus a. Right? So that difference, if we go back to the difference here, this one, which is the quadratic variation now, but when this is, we have here the square, right? So we suppose that it is order of 1/2. So this is equivalent to ti minus tj. If you take the summation, you will get b minus a, right? Okay. So in this case, the limits are different. And consequently, this integral cannot be defined by the first equation. It's have no meaning. We don't know how to define this, which is a problem, right? And now we are going to try to define this in a rigorous way. And now, of course, the second question is, are there functions which satisfy this property? You assume? So the next step now is to find functions that satisfy this property. Because we did it as an assumption before, right? So if it is the case, so the conclusion was that the limit of the Rn and the limit of the Ln are different. Now, is it possible to find functions like this? Let's see. And then we have to move to the Brownian motion. We have to move to probability. So let me introduce as simple as possible this object. I will show you the probabilistic approach, and then I will give you another way to see the Brownian motion in PDE, in terms of PDE. Okay, so this is a mathematical definition. So as I told you, this is what we call a stochastic process. You have time here, t greater than 0, and you have some parameter omega on this space. So this is a probability space. Or you can imagine a measured space, but bounded. And then you can divide by the total measure, it becomes a probability. You don't care about probability, it is a bounded measured space, right? So for each t, what does this mean? For if I fix time t, so this bt dot is a random variable. It's a measurable function. And in p, if I fix omega, this is a measurable function. And this is called the path. Okay, the trajectory. Okay, this one. Okay. So for conventional notational simplicity, we usually write p of t or p index t like this, subscript t. And many times, and in what follow, I will forget this omega. It is always there, but I will just omit it for simplification. But it is always there. So we should remember always that we have a hidden parameter in what is going on in this code. Okay. So more precision about this Brownian motion. So this is a function which starts from 0 with probability 1. So the probability that this process starts from 0 is equal to 1. And if whenever I have s less than t, the random variable pt minus bs is normally distributed. And then this means that the probability that this difference belongs to this interval ID has this as a probability this integral. So you see here the density of normal distribution, right? Okay, and we will see that this is a solution to some PDE without integral, of course. And another property which is very important is whenever you take the increment, these increments, these random variables are independent. Right? This is R independent. And we will see also that the trajectories are continuous. So the probability of all omegas for which this measurable function is continuous is equal to 1. Okay? So this is the 4 properties for the definition of a Brownian motion. Now let's see what we can do, or what is the corresponding interpretation of this function in PDE theory. So if you consider the very simple head equation, which takes this very simple form, and of course, looking at this equation, it has infinitely many solutions, right? Because now initial data and now final data, right? But if we consider an initial data, the unique solution is given by this, right? This is exactly the density of a normal distribution, right? What you see here is exactly the density of that process I defined before. Okay, so this means that if we would like to know what is the Brownian motion in PDE, I take its density, and now I am sure that it satisfies this equation. This is just a verification. You take the partial derivatives and you verify this is true, right? So this is how to take the Brownian motion in PDE theory, right? This head equation, the solution of this head equation is the density of the Brownian motion, right? Okay, more, we can also take a transformation of that one, and if you take conditional initial condition exponential, you get this one which solves this PDE, and if you have polynomials, you have Hermite polynomials as solutions and so on. Okay, more generally, if I am given any function f, right, as initial data of the previous problem, and then I can write u t x by this convolution. This is a convolution, right? This is a convolution. And this is the probabilistic interpretation of solutions of PDEs. Because I was able to write it in as an expectation of a Brownian motion plus some translation here, which is x, and then take the expectation, then I get the deterministic functions. And these deterministic functions solve the equation before. And of course, G here is the heat kernel, which is very well known in PDE. So this is the link between this, the PDE and the Brownian motion. So I may skip these slides because this is okay. So this U constructed by this way solves this PDE with this initial data. So in order, for example, to evaluate the expectation of f of dt, just solve the PDE. Right? And then evaluate and take the value at 0. U, T, 0, F. Right? So this is the corresponding part for that one. And I have also, maybe, okay, this is some properties of the Brownian motion. It is normally distributed, and the covariance is equal to the mean of S and T. Okay, so this is not really required in what follows, but I would like that to know some properties about that. I will go directly to the regularity. So this is help us to, of course, to define the integral, the stochastic integral, but I will skip it for the moment. So for the regularity, I told you about this trajectory. Thanks to this property, because the difference is normally distributed, which means 0 and variance T minus S, I can evaluate any moment of this difference to be this. So as you can remark here, you have 2k and you have here k. Right? So for k equal to 4, I have this, exactly this equality. And now, since we have an integral here, what is the regularity of bt minus s? I cannot, if I take here, for example, 1 over 2, I will get here 1 over 2. If I take here 1 over 4, I will get here square root of t minus s. But taking out the expectation, cost is costly. So this means that I cannot remove this expectation and get this regularity. So the maximum regularity I can have for this okay, so from this property, there is a result saying that the difference Pt minus Bs absolute value is less than a constant, which is a random variable, times T minus S to the power some alpha, and this alpha is less than 1/2. So the maximum regularity I can have for this Brownian motion is alpha minus epsilon. Epsilon is small enough. It cannot reach 1/2. In any case, it cannot reach 1/2. So there is no possibility there is no case to have differentiability. And using this property, we can prove that this trajectory, Bt, associate Bt as a function on time, is nowhere differentiable, but it is continuous. It is hardly continuous. And now, so it is now, the problem now is how to define this with respect to this Brownian motion. How to define it. So the case, or combining again, or going back again to Sergis integral, I will make an attempt to define this Sergis integral by the formula I showed you, by this integration by part formula. This f is continuous, this one is of bounded variation. If I assume that f is bounded variation, yes, now I can do it. I can do it omega by omega. I fix the parameter here, and then I can do it by this way, right? But what happens if f is not of bounded variation, or only continuous? Or what happens if this ft is bt itself? So I will just start by defining this in, for example, okay, this is, we can define this for f, for this function, increasing or difference of the increasing functions by the previous formula. But what happens if this is not the case? For example, you have here an unbounded function, unbounded variation function, this one. This one is unbounded variation. It's not unbounded variation, right? And so how to define this? So this is the question. And the first attempt is to define it for deterministic object. Not random. F is not random for the moment. Just constant and indicator here. So the elementary approach is just to define it for elementary functions. I will define this integral by this summation. So from 1 to n of a, I, and the difference of the bte should be this in the index.
This is
right?
One.
Sorry?
Summation.
Summation from 1.
First summation.
This one?
No, above.
Above
yeah.
Here?
Yeah, one. A sub I.
Yeah, yes, it's sub I, and this x dot should be I also.
No, but the one sub.
This is the indicator. I'm sorry. This is the indicator function. Yes, this is the indicator. Now I would like to define the integral. This one. I would like to define this integral as classically what we do is to do this for elementary functions, right? An elementary function takes the form. I will first of all take f as indicators, right? This is aj constant, and here the a indicator of ti, I minus 1, and ti. This is the indicator function, right?
And the simple function.
Yes, the simple functions, yes. Simple functions, yeah. And by this, I define this object IF by this summation. So it is linear operator and so on. And let's see what are the main properties. And the main important properties for that one are expectation of the square of that object, because I have here random variables. So I cannot do a direct calculation. I should kill randomness. And a way to kill randomness is to take expectation. So if I take the expectation of that square, objective square, I obtain exactly this. Now this is deterministic. Now I am fine. I am in a Hilbert space. I am in L2. So I have tools now to go to the limit. Okay, so maybe this requires somehow some calculations to prove this, but it is very simple. Don't really go in details. But the proof is this. The square here is exactly the expectation of that one. Right? I just take two different indices here, and then you know the product of the summation of i's all square. So I repeat the summation by taking in different indices, and no one should develop this, take expectation inside and do some calculations, but it works. Okay, so this is the details of the calculations, but at the end I get this, exactly this. So right in here I'm fine, because I was able to connect the square here, L2 in measurable spaces, with L2 in AB, right? So now I'm in a Hilbert space. Everything is this space is complete, so I can go to the limit, right? So the idea is this. Okay. So defining the inner product in L2, well, by this way, take two random variables, expectation of x, y, and then these simple functions are dense in L2. This is a classical result, right? Analysis. So and this is the way to define this. So it is possible always, once you take f in L2 AB, it is possible to approximate it by a simple function. In this way, then we define the integral by the limit of that object. And it is, of course, an is a Cauchy sequence by this isometry property you have before. Okay, so is this object well defined? We can justify very quickly that it is true. So I take the difference of two elements, ifn minus ifjn. This is, of course, because it is linear, I take just this inside, right? And then you apply the previous formula, and then this is a Cauchy in L2, then it converges, and it is fine, well defined, right? So this defines for that, so the limit, the integral a of f is equal to the limit of that object and is equal to the limit of the object. So now the definition is, whenever I have f in L2, now continuity is required. Now continuity, right? L2, then AF is defined by this object. But we have to put omega outside. I cannot do it path by path. But let me convince you that this is not possible, right? So I have to take the integral first and then apply the parameter omega. I cannot use this. This has no meaning. Because in order that this object has a meaning, PT should be of bounded variation, or this one should be of bounded variation. One of them, at least one of them. Which is not the case. F is in L2. And B, we will see. We have not yet seen that B is not of bounded variation, but we are going to see this very quickly. Okay. That's good. Oh, this is the properties of that of Wiener integrals and so on. Okay, I will skip these lines. Here. So let f be a continuous function of bounded variation. So now particular case, if I add some regularity. If it is of bounded variation, then I can define it as a surface integral. I define at the beginning by this integration by parts formula. Okay. But if it is not the case, linear integral, yeah, this is the linear integral. Yes. Okay, I will skip these lines. This is some examples of how to define this. Okay, this is just some examples considering k minus 1, for example, and so on. This is the example where we can use this relationship between surface and integral. Okay, this is the result I showed you about the regularity of B. So Bt minus S is a random variable T minus S to the power 1 over 2 minus alpha. There is no way then to have more regularity. So starting from this relation, we can just think about this B, delta B, this difference, evaluating the Brownian motion to different points. This is equivalent somehow of the order delta T over 2. So in expectation, the expectation of this delta BT is equal to delta T. So, this is exactly what measures this regularity. Okay. So let us now see what is this trajectory is. So before going over there, I would like to show you some pictures about the this how to in order to see what about the regularity of this. So this is not so okay. Maybe I can. So to see the irregularity, this is many trajectories of the Brownian motion. So it is continuous, but nowhere differentiable. So this means that it's not very obvious to plot the Brownian motion. Just you plot some trajectories of it, some realizations. Some realization of the function.
The trajectory is depending on omega.
Yes.
When you change omega, you get something.
Yeah. And at any time you simulate, you get different trajectories. At any time, you see. What I would like to show you here is that you really see the irregularity. Many points, so you see that there is no differentiability. If you have pixel like that, so this means that the trajectory is not differentiable. So this is the Brownian motion. And this is the the Brownian motion, 4 or 5 trajectories. And it is possible to do this by MATLAB, by R, by Maple. Here you have many trajectories. And it is possible to, I showed you this to see the irregularity. So let's go back again to the slides. So this is intuitively, starting from this difference is of order of delta t square of square. Sorry, this spot does not work very well. So this difference, here is of order t over n, right? If you consider this, the length of the interval is 1 over n, I consider subdivision, then this delta is of order square root. If I take the summation, this is around n square root. So this means that very quickly, intuitively, you see that the variation of the Brownian path goes to infinity. So there is no hope to guess bounded variation for the Brownian motion. But it has a quadratic variation. The quadratic variation is t. And this may connection, yes.
Sometimes when we have some divergence of the series in the sense,
yes,
instead of taking n subinterval, we take 2 to the power n subinterval. What would be happening if we take n, we take to the power n, and at the end maybe you get some series 1 over 2, 1 over 2 to the power. I don't know, I am asking you.
Yeah, I understand your question. If you take the difference here, you mean that you have here somehow to the power n, you guess to obtain here a convergent series, a convergent, yeah. But bounded variation, to get a bounded variation, you have to take the subplenum over all subdivisions, not only on one, right? To get a bounded variation function, you have to take the subplenum. For these ones, yes, we will get convergence. But for this one, is not convergent. So you have to take the subplenum over all subdivisions in order to say that this function is a bounded variation. Otherwise, it is not.
You mean whatever the subdivision that you take should be convergent?
Yeah. Yes. Exactly. in order to get the boundary variation. But for the quadratic, it is I will define what does this mean, the quadratic variation. Does this limit exist? Okay. So to see if this is really, this is the intuition, right? But we will prove if this is really true. Yeah, this is what we do here. I take this quadratic summation and I subtract t. I take its square, probabilistic tools, blah 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 blah. I will get that this converges to 0. Okay, I will not go really to go in details here, but using some techniques, we end up with this is converges to 0. So this means that this family of random variables converges in L2 to a constant. Yeah. So now the variation, this is V, this is the supremum of the difference we considered before.
Total.
Yeah, total variation. So we will prove now that if it is right of boundary variation or not. Okay. So the conclusion is the probability that this V goes to infinity is equal to 1. So this means that the difference diverges. Okay? So how to prove this? Start from this difference, from this one, and I will take one of them outside, take the supremum, classical majoration analysis. I will take the supremum here and I will get here the summation. And here I will take the supremum of all subdivisions, that is V. This is less than V, right? This one is less than V, multiplied by the supremum. But this supremum converges to 0 when the mesh of the subdivision goes to 0. Why? Because of the continuity of B. So here we really need the continuity of B. So this means that this quadratic variation is equal to 0. But we have proved that it converges to T. It's not possible. Because we assume that it's finite. If this is finite, right? If this is finite, so this will converge to 0. This is a contradiction because we have proved that it converges to T. So there is no way to define it as a Selgis integral. Now, to understand that there is no possibility to define the stochastic integral using Selgis integral is to use this very nice theorem. There is this characterization, this summation Sn I define here as a Riemann sum or whatever you call it, is if this summation converges for all continuous bounded function f. This is equivalent to say J is all bounded function. This is a very nice theorem. Very nice theorem. So the proof, I will not go in the proof, but it is very nice application of the Banach-Steinhaus theorem. Very nice application. Okay, believe me, that is true. Now, I will maybe finish by this slides. This is the first question. Maybe there is only also 5, but I think that there is no time maybe not to take you more. Okay, so of course we understand from that there is no way to define this integral by Selgis because B is not a bounded variation. If I assume that this Sn converges for B, I will end as a conclusion, I will get B a bounded variation, which is not true. So there is no possibility to do that. Now let's go back to what I defined at the beginning, this summation Ln and Rn. This is the left-hand point of the interval, and this is the right point of the interval. Okay, this is discrete summation. Now this is random and this is random. Before, we defined this for deterministic and deterministic. Here, it was okay. Whatever the endpoint you take here, it doesn't matter. But now here, for stochastic integral or for equal integrals, it is important. And we will see how this is important. So taking this summation and go back to the calculations we had, this difference is what we have seen already. This is the quadratic variation. And we know that this quadratic variation converges to P minus A. Because I took at the beginning the interval 0, T. And now here AB. So it is the same. Okay. So this is details and so on. This is how to define this integral. AB squared, take this square of this difference and so on. Okay, this is not a problem. So go back again to this summation and the difference. The summation gives me that one. If I develop, I will get this. And this I will end up with this one. Rn is this one and Ln is this one. Right? Now if I take the limit of Rn and limit of Ln, this is because I know this is the quadratic variation converges to Riemann-Selling. These two quantities here. Plus here, minus here. Okay? Then we will end up with this. So finally, I was able to get an interpretation of that summation. So this means that this Rn, remember that this Rn quiz, this is Rn. This is right hand and this is left hand, right? Good. This terms here, I just can write here the integral from a to b of du dbu. And this one also. So since this limit exists, what does this mean? But they are different. This means that there is the possibility to define this integral. In this simple case, yes? Okay, I got a limit. Okay, this means that A can use one of them as an approach to define the successive integral. This is the fifth question. Which one I'm going to write? So if I write here the right hand side and the left hand side, LT, the limit of Ln, and RT, the limit of Rn, right? So this is the two possible objects I can define from that integral before. Now, from this at this step, one has to choose which one will be appropriate when you consider functions of Bt. If I integrate, we integrated the Bs in front of dBs, right? With respect to dB. But now if I would like to integrate a function of Bt, could be square, could be sinus, could be exponential, whatever this function is. A function of Bs, dBs, as in integral, right? So I will just explain to you the idea here. If you take the expectation in the right hand side here, you get t. If you take the expectation of R, you get 0. Okay? So this one is more convenient in general situation. This one, which gives the mean is equal to 0. Because this contains an important property, which is Martingale property. Yeah. So this Martingale theory is a big subject in stochastic calculus, but it helps to make a connection between PDEs and stochastic processes. But this is the area. But this one is not a martingale. This one is not a martingale, and this is a martingale. What is a martingale? What are the properties of a martingale? If you take the expectation of a martingale, you get a constant. Always constant, if it is a martingale. If it is not a martingale, it is not constant. For example here, it is not constant because it is linear NT. But whenever you take expectation of a martingale, you get a constant. You get expectation of M naught. And this is what I wrote here. The conditional expectation of LT with respect. This is something else. This is conditioning and so on. You have to define conditional expectation and so on. So this is at least the answer of four questions. And there is no time to show you why A cannot integrate this.
We can do the next step. Sure.
Yes, no problem. For me, no problem. If people would like to continue, I can do it. But not now.
Not now.
I mean, otherwise, yes.
Yeah.
Maybe there's some problem.
Yeah.
I think that we will have to stop here, and thank you very much.
Thanks a lot.
Thanks. Nice.
Assalamu alaikum. If you have questions, please don't hesitate to ask me.
Anyway, I have many questions.
Yes, I'm welcome.
I mean, if you have time.
Yes.
So the first question. Till now, I understood why this the right hand side is not well defined using the theorem.
Yes.
And that one till now I cannot see how it's defined.
Which one?
The left.
This one.
Yeah, the left. I try to follow.
Yeah, this one is exactly LN, left hand side. Left.
No, I mean you fix your omega
Yes.
and you are.
Yes. Omega, I will not touch omega. I have to define this object. No, this is L. This is the limit. No, the definition of that object is the limit of the summation of BTI times BTI plus 1 minus BTI. It should be, you should evaluate the integral at the left end point. This is the main area for A2 integral. Once you do this, your integrals, your summation converges. And it converges to ايش؟ خليني اقول لكم شويه هذا اللي احنا قلناها this difference هذا this difference. This is R, right? This is there's something is missing here. I should multiply by 2 here. If I put 2 here, the difference is T. The difference is T. Okay. So this is, as I told you, this is L. This is L of T. This is L of T. So why I cannot interpret this as this?
Yeah.
By this theorem, I tell you.
Yeah.
So there is no way. So I have to take it outside. Stop.
No. I mean, I'm not looking for the right hand side.
Yeah.
The right hand side, it's okay. It's
Yeah.
very clear. I mean, the well-definedness of this term, of the left one.
Yeah.
Remove the omega or W.
Yes, I will remove this one. This is defined as the limit of the Riemann sum, but evaluated at the left-hand point. There is no omega. This is one thing. Moreover, you can evaluate it. This is equal pt squared minus b naught squared
It's well-defined.
over 2. Yes, over 2 plus t.
I have no-
This is the formula. I will maybe do it next time. You will understand more.
Oh, I have another question. When you take the case, your G is C1.
Yes.
Your function is C1.
My function is C1. Yes.
Yeah. If you can go to that
Yes.
slide,
Yes.
please.
Yes. Yes. Yes.
Use the arrow.